This is the 12th video in a series devoted to abstract linear algebra. And we just did a bunch of videos regarding vector spaces and bases of vector spaces. And we're going to wrap up all of that information in this video before we launch into the theory and structure of some linear transformations. So before we get going, let's recall the definition of a basis. So let's suppose that V is a vector space over an arbitrary field K. So we've been working with fields of rational numbers, real numbers, complex numbers, or integers modulo p, although there are more fields out there, but those are the ones we're sticking to. So we say a subset B of V is a basis of V if B is linearly independent and the span of B is the entire vector space V. So let's recall some examples that we've seen before and maybe look at a couple that we haven't seen before we get going with like some wrap-up results regarding bases. So the set of standard basis vectors forms a basis of Kn. So here we have E1, E2, E3, E4, so on and so forth, all the way up to En. So what do I mean by EI, for instance? Well, let's just do an example. E1 would be 1, 0, and E2 would be 0, 1 if we were considering all of this happening in K2. So the space of like ordered pairs. So in other words, EI is the vector whose entries are all 0 except in the ith component where you get a 1. Okay, now here's an example that we haven't looked at before, but it's fairly simple. And that is the real number 1 and the imaginary number I forms a basis for C over the real numbers. So the complex numbers here is the vector space and the ground field is the real numbers. And this is kind of clear that this works because you can write every complex number as a linear combination of these two things. In fact, you can write it as A plus BI, where A and B are in R. So that's the definition of the complex numbers. That's kind of naturally rewritten as a linear combination of these two basis vectors, or basis numbers here. So our next example is an infinite dimensional version, and that's the monomials 1, which is of degree 0, x, which is of degree 1, x squared, x cubed, x to the fourth, and so on and so forth, is a basis of k adjoin x. So that's all polynomials where the variable is x and the coefficients come from the field k. Then there's kind of a finite version of that, given by the monomials 1x, x squared, ending at xn. That's a basis of something that we've been calling Pn, although we've changed the notation throughout the videos. I think we're going to settle on this. So let's recall Pn is all polynomials of degree less than or equal to n. It's pretty easy to see that the dimension here is n plus 1. That's because you get every power of x from 1 to n. That would be n total vectors here. The monomials are playing the role of vectors. And then you've got this constant 1, so n plus 1. And then kind of an esoteric example down here, which is outside of the scope of our goal here. But there is an uncountable basis of the real numbers viewed as a vector space over the rational numbers. So uncountable means we can't like list this out in any reasonable way. But I just put this here kind of for a nice bit of trivia. Okay, so now that we've warmed up our minds and recalled some of these notions, let's jump into our wrap-up results for bases. So before we get going with today's result, I want to point out that for the rest of this video, we're only going to consider finite dimensional vector spaces. When you do this kind of stuff with infinite dimensional vector spaces, some sort of subtlety gets into the whole setup that is not really in the scope of our goal here. Okay, so let's look at this first result. It says that every linearly independent set of vectors of a vector space, so that's unwritten, but you would read that in there, can be extended to a basis. And then our second statement here is every spanning set can be contracted to a basis. So linearly independent sets might be too small, so they have to be made bigger, whereas spanning sets might be too big, so they might have to be made smaller, until you get just the perfect balance, which gives you a basis. Okay, so let's look at this first statement. And let's really see what this means first. So let's say here we have V is a vector space. So I'll say a vector space over our field K that we're working with. And then what this is saying is that for all linearly independent sets S, which are subsets of the whole vector space, there is a basis B such that S is a subset of B. So S is a subset of B. Whatever is in B that is not in S can be seen as what is the extension here. So we had to extend S until it was all the way up to B. So let's maybe just put this in a box. And this is just rewriting that number one. Okay, and now that we've rewritten number one, we can get to proving it. Okay, so let's suppose that we have a set, I'll call it S, which is V1 up to Vm, is a subset of V is linearly independent. Great. And I guess we should maybe put a dimension to V. So we're assuming that V is finite dimensional. So let's just say that we have the dimension of V equals N. Okay, nice. And now what should we do from here? Well, we have really two cases to break this into. So let's look at case number one, which case number one is actually the already done case. And that would be the span of S equals the entire vector space V. But then S is linearly independent and it spans the entire vector space. But that's exactly the definition of a basis over here. So we would say S is equal to B. Okay, so that case is not super interesting. So let's move on to our second case, which is that the span of S is not equal to V. Okay, but what does that mean? So that tells us that there exists, I'll maybe call it W1, which is in V, such that W1 is not in the span of V, like that. Okay, nice. Now, what do we want to do from here? We want to extend S by this vector W1. So let's define S prime to be equal to V1 up to Vm and then W1. So that's our first extension vector. And now we'd like to argue that S prime is also linearly independent. So let's do that down here with a claim. And this is actually not super hard. And so S prime is linearly independent. Okay, so how do we do that? Well, we try to build a linear dependence relation and see that the only way to do it is with all of the coefficients being equal to 0. So we'll look at alpha 1 V1 plus up to alpha m Vm equal plus beta times W1 equals 0. Great. And now let's notice we've got two cases. The first case is if beta is equal to 0. But if beta is equal to 0, then alpha 1 through alpha m is also equal to 0 because our original set was linearly independent. So that moves on to our second case, which is beta is not equal to 0. But then notice if beta is not equal to 0, then that means we can solve for W1 in terms of V1 up to Vm, which tells us that W1 is indeed in the span of V, which we know is not true. So in other words, beta has to be 0, which proves that this has to be linearly independent. Okay, so I did that with words, but maybe like write down all of the details if you feel like you need to. We did a argument like this in the previous video, so I don't feel so bad about it. Okay, so anyway, we've got S prime is linearly independent. Okay, so let's maybe get rid of this down Okay, so let's maybe get rid of this down and then we'll finish the argument for number 1. Okay, let's recall what we did. We took a set of linearly independent vectors S, V1 through Vm. We assumed that it did not span the entire vector space because if it did, we would be done. And so we took an element outside of its span, we called it W1, and then we extended this set by that vector W1. We called it S prime. So that's going to be V1 up to Vm and then W1. Then we proved that was linearly independent as well. Now we're going to repeat the process on S prime. So let's do case 1 on S prime, which is the span of S prime equals the whole vector space. But we have up here that it's linearly independent. If it spans the whole vector space, then we can set our basis equal to S prime, and we'll note that S is most definitely a subset of S prime, which is the basis, and we're done. We have extended our original set of linearly independent vectors to a basis. But that's only if the span is the whole vector space. So we need to move on to case 2, which is the span of S prime is not equal to V. That tells us that there's another vector from V that is not inside the span. So there's a vector, I'll call it W2 in V, such that W2 is not in the span of S prime. And then we're going to do the same thing that we did before. Let's define a new set, S double prime, which will be equal to V1 up to Vm, and then W1, W2. Great. Now I'll make the same claim as before. Claim is that S double prime is linearly independent. And that proof goes exactly the same way as the one that we sketched out on the last board. So this will be linearly independent, and then we go through these two cases again. So we want to repeat this whole process. And this would be a sticky endeavor if the dimension was infinite, but since the dimension is finite, this will end eventually, because the dimension of V is less than infinity, right? We're adding a vector each time, right? And if you can never stop that, you'll end up adding infinitely many vectors, and then you have an infinite dimensional vector space. But since V is finite dimensional, this process has to stop. But along the way, we've created this string of subsets that are all included in each other. So let's say this stops after doing it maybe k times. So if this stops after k times, we would say S upper K is equal to our basis. And like I said, we've got this string of inclusion. S is inside S prime, which is inside S double prime, which is inside all the way up to S upper K, which is equal to the basis. And we've successfully extended our linearly independent set to a basis, which is exactly what we needed to prove this first result. Okay, nice. So let's get rid of this and then we'll do the same thing for the second result. Okay, so now we're moving on to our second result, and you'll see that this has the same sort of flavor to it, except instead of adding a new vector in, we'll subtract one in. Okay, so let's get going. So let's suppose that our set S, which I'll call it V1 up to Vn this time, spans our vector space V. And then this is going to turn into two cases just like before, but instead of the cases being do you span V, the cases will be are you linearly independent. So case number 1 is S is linearly independent. But if it's linearly independent, then we can just set S equal to the basis itself, because we've got something that's linearly independent that spans, but that's exactly the definition of a basis over here. So that means we really just need to move on to this second case, which is S is not linearly independent. But remember, we said that something was not linearly independent if it was linearly dependent. Great. But if it's linearly dependent, then we can write down a linear dependence relation. So that means there exists alpha I in K, not all 0. So that's the important part, that they're not all 0, such that we have, like I said, a linear dependence relation. So this will be alpha 1 V1 plus up to alpha n Vn equals 0. Okay. And then while we're at it, I'm going to do a little bit of a trick just to make everything work out a little more nicely. And this is a trick that we did in a previous video. So if these are not all 0, what I can do is I can just rename the elements V1 to Vn so that alpha n is the one that's not 0. So let's do that. So rename or reorder, I don't exactly know which word you guys would like to use, but let's rename the VI's so that the alpha n is the one that's not equal to 0 in this relation right here. So again, that's just renaming. If you want to get really picky about it, you could introduce some sort of superscript on the V's to count how many times you've renamed, but I don't think we really need to do that. Okay, nice. But now, if alpha n is not equal to 0, then that means we can solve for Vn. So let's see. Vn is equal to minus 1 over alpha n times alpha 1 V1 all the way up to alpha n minus 1 Vn minus 1. But that's a linear combination of V1 to Vn minus 1. That means it's in the span of the set V1 up to Vn minus 1. Great. But if S, which is V1 up to Vn, spans the whole set, and Vn can be written as a linear combination of the lower vectors, then that means V1 up to Vn minus 1 actually also spans the whole set. So we'll set S prime here equal to S set minus Vn. So in other words, it's just V1 up to Vn minus 1. Great. And we could maybe say that as a claim before, but we don't really need to do that. I think we said it in words nicely enough. S prime spans V because of this relation right here. Okay, now what are we going to do from here? We're going to repeat this process again. So is S prime linearly independent? If so, we're done. If not, we'll take out another vector. And we'll continue taking out vectors until we're done. And we know that this will finish after a finite number of steps because we started with a finite number of vectors in the first place. So here the finite dimensionality started at the beginning instead of showing up in the end. Okay, so I think this is good. Let's get rid of this and look at something kind of profound that follows from this that we may not have even thought of. So in the last video, we defined the notion of the dimension of a vector space. So the dimension was the number of elements in the basis. But we never really defined what it meant to be just finite dimensional without that number being less than infinity. And so let's do that right now and really talk about why it's important. So we say a vector space V is finite dimensional if it can be spanned by a finite number of vectors. So notice this doesn't say anything about the existence of a basis. And in fact, a priori, we're not even sure that all of these V's that are finite dimensional have a basis. In fact, there are algebraic structures where you could have a finite spanning set that can never be pared down to a linearly independent set, as we saw was possible all of the time with vector spaces. And that brings us to this very, very quick corollary to what we just saw, and that is every finite dimensional vector space has a basis. That means there's a notion of a dimension to every finite dimensional vector space. And I know I'm using the word dimension for the number of elements in the basis vector and finite dimensional for being spanned by a finite number of vectors. And the word dimension is being used twice there, but you can think about these concepts as two separate things. So finite dimensional is one idea, which is spanned by a finite number of vectors. And the dimension is another idea, which is the number of elements in a basis. But this corollary to that previous theorem says that if it's finite dimensional, then it has a dimension. What's that dimension? The number of elements in the basis, which again, we're guaranteed to have by the previous theorem. So I hope I did a good job like going over the subtlety of that. But this is actually really important and what separates vector spaces from some other algebraic structures, maybe namely modules over a ring, which is maybe like something you'll hear about in a later course. Okay, so anyway, let's get rid of this and look at some other kind of results that are equally subtle that come out of these kind of ideas. So our next subtle result says that if we have a vector space V and a subspace W, recall we're only working with finite dimensional vector spaces, then the dimension of W is less than or equal to the dimension of V. Okay, so this proof is pretty quick based on that last theorem, but let's see how it goes. So let's take a basis of W. And this is something that we were not really able to do until we proved that last theorem and the corollary that came with it, because W is a vector space on its own, so it has a basis. So let's call that basis BW, and maybe it's equal to W1 up to WM. But since W is a subspace of V, and these are all vectors from W, that makes this a subset of V. So let's write that here. This is a subset, not a subspace. Okay. But notice, not only is it a subset, but it's a linearly independent subset. Linearly independent. So how do we know it's linearly independent? Well, that's because it's a basis for W. And any basis for W will be linearly independent and it will span W. It doesn't have to span V though, because it's a basis for the subspace W. Okay, so anyway, what do we want to do now? Now let's apply the last theorem to extend BW to a basis of the whole vector space. So that basis of V. So let's maybe call this B. Great. And now let's notice that BW will be a subset of B. Great. But these are both finite sets. We know they're both finite sets because we're in a finite dimensional space here. Okay, so if you've got two finite sets, one is a subset of the other, then the cardinality, or the number of elements in this set, will be less than or equal to the number of elements in this set. But the number of elements in BW is the dimension of W, and the number of elements in B is the dimension of V. And that's all there is to this theorem. Okay, so let's look at a couple more results and then we'll do some examples. So I'll present the next couple of results without proof, as they follow very, very quickly from the theorem that we previously proved about a linearly independent set being extendable to a basis and a linearly dependent set being contractible to a basis. So let's look at this first one. So we start with an n-dimensional vector space V and a set of m vectors, V1 through Vm. And those are vectors in V. Then if m is bigger than n, then S is linearly dependent. So why is that? Well, let's quickly assume otherwise. If S was linearly independent, then it could be extended to a basis of V, but that basis of V would contain S, and thus it would have more than m vectors, but that means the dimension of V would be bigger than m, but it's already said to be less than m, so that would be a contradiction. And then here's kind of the dual statement to that, and that's if m is less than n, then the span of S is not equal to V. Again, you could do the same kind of thing here. If the span was equal to V, then we could contract S into a basis, but that basis would have less than m elements, but then we've contradicted the inequality again. Okay, then here's a nice theorem. I can't like really punctuate the niceness of this theorem enough because it allows us to only check one of the properties of a basis if you know something about the dimension. So again, we start with an n-dimensional vector space, and let's say we've got a set of vectors, I'm calling them B, which is v1 through vn. So we've got n total vectors, it's n-dimensional, that's important. Then the following three statements are equivalent. B is linearly independent, the span of B is V, and B is a basis. So what this means is if you have the correct number of vectors and you know the dimension, you only have to check linear independence or spanning in order to prove that it's a basis. Often it's easiest to check linear independence. So this is actually a nice quick way of checking both of the conditions for a basis just by only checking one and then using this theorem. And again, the proof of this theorem will rely on that extension contraction theorem just like before. So if B is linearly independent, it can be extended to a basis, but it already has n elements, so every basis will have n elements, so that means it doesn't need to be extended at all, which means it's already a basis, and then so on and so forth. Okay, so now that we've gotten this taken care of, let's maybe get rid of this and we'll look at some examples. So for our first example, we've got a set of three vectors, 1, 0, 0, 1, 1, 0, and 1, 1, 1, thought of as a subset of K3, where K is an arbitrary field. So this is the right number of vectors to be a basis. So that means we only really need to check if it's linearly independent or if it spans, and then we automatically know it's a basis. But these are kind of clearly linearly independent, which means this is a basis for K3. We could quickly check that this is linearly independent just by taking a linear combination. So x times 1, 0, 0 plus y times 1, 1, 0 plus z times 1, 1, 1 equals the 0 vector. And then transform this vector equation into a system of equations. That system will look something like this. X plus y plus z equals 0. That's from the first entry. Then y plus z equals 0. That's from the second entry. And then finally z equals 0. That's from the third entry. But check it out. If z is equal to 0, then that means y is equal to 0 because we have y plus 0 is 0. But then if y and z are 0, then x is 0 as well. So here we get x equals y equals z equals 0, but that's exactly the condition that we need for this to be linearly independent. And then like I said, we've got three linearly independent vectors, a three-dimensional vector space. That means it is indeed a basis. Okay, so let's maybe clean this up and we'll do another similar example. Now I've got another example. So we've got three vectors in R3. So 1, 2, 3, 1, 3, 2, and 1, 0, 0. So I'll let you guys check using similar methods to what we saw before that these vectors are linearly independent and since there are three linearly independent vectors in a three-dimensional vector space, that makes them a basis. But now let's check these same vectors if we view them over F5. Remember the field of 5 elements. So we're in F5(3). So let's try to build a linear dependence relation and see if it works here. So we have x, 1, 2, 3, plus y, 1, 3, 2, plus z, 1, 0, 0 equals the 0 vector. Okay. So let's see what we have. We'll have x plus y plus z equals 0. So that's from the first component. And then next we'll have 2x plus 3y equals 0. And then finally down here we'll have 3x plus 2y equals 0. But now notice here, this tells us that 3x equals, I could write this as negative 2y, but negative 2 in F5 is the same thing as 3. Because 3 plus 2 is equal to 5, but 5 is equal to 0 in F5. But now we can multiply by the multiplicative inverse of 3. That's 2 in this case. If we multiply both sides of this equation by 2, we'll get 6x and 6y. But 6 is 1 in F5. That gives us x equals y. Okay, so now let's take x equals y and throw it into this second equation and see what happens. So if we throw that into the second equation, we'll get 2x plus 3x equals 0. But then let's notice that that is always true, because this is the same thing as saying 5x is equal to 0, but 5 is equal to 0 in F5. So this is true for all x. So we could just pick a non-zero x, and that will build our linear dependence relation. Let's maybe pick x equals 1. Then so x is equal to 1, so we can scrub that out and scrub that out. But then going back to this equation, we have 1 plus 1 is 2, plus z equals 0. So that means z has to be equal to -2 or 3 in this case. And now we can check that this is indeed a linear dependence relation. In the first entry, we have 1 plus 1 plus 3, which is 2 plus 5, which is 0. Here we have 2 plus 3, which is 5, and that's 0 in F5. And then the same thing happening in this third component as well. Okay, so let's maybe get rid of this, and we'll look at one other quick example and then give you guys some warm-up exercises. So here's two examples that follow directly from one of our theorems. The first is that if we have 3 vectors in K2, a 2-dimensional vector space, then these 3 vectors must be linearly dependent. Why is that? That's because K2 must have a basis of 2 vectors. But if these were linearly independent, then it would have a basis of more than 2 vectors, which is a contradiction. Okay, now what about this? If we've got W1, W2, and W3 are all vectors in K4, then the span of W1, W2, W3 cannot be the whole space. So it will be a proper subspace of K4. I've written it like this. So it's a subspace but cannot be equal. And why is that? Well, again, K4 is 4-dimensional. If this did span the whole space, then there would be a problem with the number of dimensions there. Okay, nice. So let's get rid of this, and then we'll end with some warm-up problems. So here's some nice warm-up exercises based on what we did today. So the first is to show that these 3 vectors, 1, 7, 1, 1, 0, 1, and 1, 2, 3, form a basis for R3. And then find a prime so that these do not form a basis of FP3. So this is pretty similar to one of the examples we looked at. And maybe there are multiple primes. I think it would be interesting to classify all primes where this is not a basis. I think that's maybe a nice bonus question. Next, show that the set of polynomials 1 plus x, 1 minus x, and 2 plus 3x plus x squared is a basis of P2. Remember, that's polynomials of degree less than or equal to 2. So this says if we have real coefficients, but then answer the question again if there is a prime P where we're taking those coefficients to be in the field FP. Okay, and then finally, here's another kind of nice proof type exercise, and that is show that V1, V2 is a basis of V if and only if V1, V1 plus V2 is also a basis for V. And that's a good place to stop.